Hey guys, my name is IBM and today I'm introducing dynamics, and I think dynamics, this is going to be lesson one. Do not forget, in dynamics the major areas we talk about are basically Newton's laws of motion and then momentum or linear momentum. So we shall talk about kinematics. By the way, I'm supposed to teach kinematics before dynamics, or you're supposed to learn kinematics before dynamics. The topics in the introduction of this video are in the order in which they are supposed to be studied. So if you have not studied them, you should study them in that order if you want really to understand them very well. Apart from particle physics, which you can start at any stage. So in dynamics, we shall concentrate majorly on Newton's laws of motion and linear momentum. That's what makes this unit a little bit easier because it relates to some of the concepts you studied in IGCSE. So what is dynamics and what differentiates it from kinematics? In kinematics, your teacher must have told you that kinematics was concerned with describing motion without minding about what affects the motion. But in dynamics, we shall actually describe, or we shall be concerned with the problems involving motion or with the problems that affect motion. So let's start with the force, motion, and mass under dynamics. So dynamics is going to be concerned with what exactly affects or causes motion. For example, we shall talk about force that affects motion, or the effect of force on motion. That is the concern of dynamics. So when you push or pull an object, you are exerting a force on the object. And we may have defined the force in a unit called force density and pressure as the rate of change of momentum. So the force you are exerting can change dimensions of the bodies. Force can change dimensions of bodies in a reproducible way. Therefore, it takes the same force to stretch a spring by the same length. For example, I could simply say that a spring balance can be used to measure force in the laboratory. So the laboratory spring balances are often used to measure weight, which weight is a force, and you normally call them Newton balances because the SI unit of force is the Newton. But it would take the same force to stretch a spring by the same length. That's why we are using the spring balances in the laboratory to measure weight. Yet weight is a force. Only that the spring balances are calibrated in newtons. So your teacher must also have told you, or you must have developed an understanding that forces are vector quantities, and therefore they have both magnitude and direction. And a number of forces acting on a body are often shown by means of a force diagram, which could be drawn to scale, as we saw in a unit called force density and pressure. So as drawn to scale, in which the forces are represented by lines of length proportional to the magnitude of the force and in the appropriate direction. In force, density, and pressure, you may also have mentioned that the combined effect of several forces acting on a body is known as the resultant force. So in this unit of dynamics, we might need to understand the concept of force that we described under force, density, and pressure. But in dynamics, there are three figures we need to mention, or there are three important people we need to mention. One is Aristotle, Galileo, and finally Isaac Newton. These are the people behind the concepts we are going to discuss in dynamics. To begin with, Aristotle, a Greek philosopher, believed that the natural state of a body was a state of rest, and that a force was necessary to move and to keep a body moving. The natural state of a body, according to Aristotle, a Greek philosopher, was that the body was supposed to be at rest. And to make it move and to keep it moving, it was necessary that a force is applied. This argument suggests that the greater the force, the greater the speed of the body, according to Aristotle. If the natural state of a body is when it is at rest, and that to make it move, we must apply a force, and to keep it moving, we must apply a force, then the argument that the greater the force, the greater the speed of the body can be considered to be true. But then later on, another scientist in the name of Galileo Galilei questioned Aristotle's idea and suggested that the motion at a constant speed could just be as a natural state as the state of rest. Motion at a constant speed could be just as natural a state as the state of rest. So Galileo is arguing that even when the object is moving, as long as it is moving at a constant speed, the motion of such a body is also as natural as it is when the object is at rest. You might have experienced this in everyday life. If you are inside a car and it is moving at a constant speed on a smooth road, you can throw an object vertically upwards and it comes vertically downwards. The same thing would happen if you were standing on the Earth's surface, throwing an object vertically upwards to come back vertically downwards to you. But remember, in the first case, you are in a car which is moving. So it's like Galileo's argument could also be accepted. So he suggested that the motion at a constant speed could be just as natural a state as the state of rest. So he then introduced an understanding of the effect of friction on motion. Imagine you push a heavy box, or imagine a heavy box is being pushed along a rough floor at constant speed. This may take a considerable force, of course. The force required can be reduced if the floor is made smooth and polished, and reduced even more if a lubricant such as oil or grease is applied between the box and the floor. So this implies that as friction is reduced to a vanishingly small value, the force required to push the box at a constant speed is also vanishingly small. So Galileo's argument also led to the introduction of the concept of friction between two surfaces that are in contact. And analyzing his argument, we can conclude that if the friction is small, then we require a small force to push an object at a constant speed. Thus, Galileo realized that the force of friction was a force that opposes the pushing force. That's why when you are in a moving car and you put your head through the window, you feel more wind blowing if the car speeds up or if the car is moving at a high speed. So, when an object moves at a constant speed, the pushing force is exactly equal to the frictional force or the opposing force. But these two are in the opposite direction. So there is a net force of zero acting on the body or on the object. So therefore, there are two natural states of a body, according to the Galileo. He did not distort Aristotle's argument, but he also established an understanding that even when an object is moving, As long as it's moving at a constant speed, it is also in its natural state. Everything else within everything else within the object or everything else on the object is as natural as it would be if the object was at rest. And this led to what we call the theories of relativity and so on and so forth. So a body is in its natural state if it is at rest or if it is moving at a constant speed. And later on now, Isaac Newton Isaac Newton developed Galileo's ideas to come up with a theory of motion which he expressed in the three laws that we shall later on call Newton's laws of motion. So Sir Isaac Newton is known for developing Galileo's ideas to come up with a theory of motion expressed in his three laws, which are the famous laws that we are going to discuss in the unit called dynamics. So like I said, the unit of dynamics rotates around three scientists: Aristotle, a Greek philosopher, Galileo Galilei, and finally Isaac Newton. So Aristotle was arguing the natural state of a body is when it is at rest. It will only move when a force is applied. And if we want it to speed up, we should increase, or if we want to maintain its motion, we must continue applying the force. Then Galileo is arguing that, okay, it is true that the natural state of a body is when it is at rest. However, observations show that even when a body is moving at a constant speed, it is as if it is in its natural state. And by the way, it was easy to verify that the laws of physics could apply on a body which is moving uh, at a constant speed. You could play football in a moving train if it is moving at a constant speed on a smooth road. And finally, Isaac Newton now combines the ideas of Galileo. He combines the ideas of Galileo with Aristotle and comes up with his famous three laws of motion, which we call Newton's laws of motion. So in this unit, we are just going to explore Newton's laws of motion. Let's talk about Newton's laws of motion. The first law of motion. Whenever I write any1, any2, any3, I'm actually referring to Newton's laws. Any1 is Newton's first law, any2 will be Newton's second law, any3 will be Newton's third law. So Newton's first law. So the first law rewrites Galileo's deduction about the natural state of a body, or Galileo's conclusion about the natural state of a body, that everybody continues in a state of rest or moving with a uniform velocity unless acted upon by a net force or a resultant force. Every object will either stay at rest or it will continue moving with a constant velocity or uniform velocity unless acted upon by a resultant force. Of course, if there is a resultant force, we expect that there is an acceleration. And if there is an acceleration, then the speed or the velocity cannot be constant. However, if there is no resultant force acting on a body, or if there is no net force acting on a body, the object or the body will continue in its state of either rest or moving with uniform velocity in a straight line. And this is what we call Newton's first law of motion. Of course, these laws are applying to linear motion, that is motion in a straight line. So this law tells us that the effect of force, that it disturbs the state of rest. If you apply force on a body at rest, the force disturbs the state of rest. It disturbs the velocity of a body. If you apply a resultant force on a body, then the body is going to accelerate. So it is normally called the law of inertia. What do we mean by inertia? Inertia is a property of a body to stay in a state of rest if it was at rest, or to continue moving with a uniform velocity if it was moving in a straight line. That is what we call inertia. There is a natural tendency of bodies to continue with their state of rest if they were at rest, or to continue moving in a straight line if they were moving with a uniform velocity. That's why if you're in a car and the brakes are suddenly applied, you tend to jerk forward, to move forward. That's why you are always advised to put on seat belts. That's what we call inertia. So from this law, from this law, force is the action which is able to create a change, to create or change motion. So according to the first law, if there is a force, a resultant force acting on the body, then it is going to cause a change, it's going to create motion, or it is going to change motion. That is Newton's first law. Every object or every body continues in its state of rest or moving with a uniform velocity provided or unless unless a resultant force acts on it, or provided no resultant force acts on it. That is what we call Newton's first law. You should be able to state Newton's first law. An object continues in its state of rest or moving in a straight line with uniform velocity if no resultant force acts on the body. If no net force acts on the body. That is Newton's first law. Let's explore Newton's second law then. Now, this law, Newton's second law, tells us what happens if a force is exerted on a body. What really happens if you exert a force on a body? So this law tells us what happens if a force is exerted on a body and what actually happens. By the way, force can change direction, a force can change, and of course, if direction changes, a force can change velocity. So forces cause a change in velocity. It causes a body at rest to move, or causes a moving body to speed up, or to slow down, or to change direction. Those are some of the effects of force. Since changing velocity is actually with the time is acceleration, this law relates the magnitude of the acceleration to the force applied and also introduces the idea of mass of a body. So we know that acceleration from kinematics is the rate of change of velocity. So Newton's second law um, relates the magnitude of the acceleration to the force. That's why every time I say F is equal to ma, F is going to be the resultant force and A is the acceleration. So the second law relates acceleration to the force applied, and it introduces the idea of mass of a body. So how do we define mass from this law? Because in the first law we saw that there's a natural tendency of bodies to resist. There's a natural tendency of bodies to maintain their state of either rest or continue moving with a uniform velocity. So the second law is actually going to give us the definition of mass, relating it to the first law. So very massive objects will offer much resistance to change their state of motion or their state of rest. Therefore, we can define mass as a measure of inertia, of a body to change in velocity. Remember, inertia is like a resistance to change in the state of motion or state of rest of a body. So mass can be defined as a measure of the inertia of a body to change in velocity or to change its velocity. Because inertia relates to resistance, we can say mass is a property of a body that resists change in motion, and that is the best definition of mass. Of course, it doesn't take away the fact that you can define mass as the quantity of matter in a substance. But the best definition would be mass is a property of a body that resists change in motion. Of course, this means that the bigger the mass, the more difficult it is to change its state of rest or velocity. It is easier to stop a moving bike than to stop a moving truck because the moving bike would be having a smaller mass, so its inertia is also very small, but a big truck is having a large mass, so its inertia is also going to be large. So when we talk about mass, we are referring to a property of a body that resists change in its motion, a property of a body that resists change in motion or change in the state of motion of that body. That is what we mean by inertia. Okay, so how do we state Newton's second law? Therefore, Newton's second law will therefore be stated that for a body of constant mass, that is, we keep mass constant, its acceleration is directly proportional to the resultant force applied to it, and it takes place in the direction of the force. That's why many times in calculation I will say by Newton's second law, F is equal to ma. If the mass is constant, the resultant force is directly proportional to the acceleration. The resultant force and the acceleration both act in the same direction. So for a body of constant mass, its acceleration is directly proportional to the net resultant force, to the net force or the resultant force applied to it. The two, that is the acceleration and the force, the resultant force are in the same direction. So the acceleration takes place in the direction of the force. Alternatively, we can define this in because force is the rate of change of momentum or the resultant force is the rate of change of momentum, then we can say the net force acting on a body is directly proportional to the rate of change of its momentum. The net force acting on a body is proportional to the rate of change of its momentum. The force here is the net force. The net force is the resultant force. So of course, because force is a vector quantity and momentum is a vector quantity, the net force and the change in momentum are supposed to be in the same direction. The change in momentum or momentum of a body changes in the same direction as the net force acting on the body. That is Newton's second law. And of course, from this law, we know that our force is measured in newtons and mass is measured in kilograms. Acceleration is measured in meters per second. So we can define the Newton because I think we might have defined the Newton under force, density, and pressure. But if force is measured in newtons and m in kilograms, acceleration in meters per second squared, then a Newton could be the force which gives a mass of 1 kilogram and acceleration of 1 meter per second squared. So a Newton is defined as the force which will give a 1 kilogram mass and acceleration of 1 meter per second squared in the direction of the force. The force which will give a 1 kilogram mass and acceleration of 1 meter per second squared in the direction of the force. That's what we mean by a Newton. So that is Newton's second law. The net force acting on a body is directly proportional to the rate of change of momentum. The net force and the rate of and the change in momentum are in the same direction. That is Newton's second law. Then we should now talk about, I think we should talk about Newton's third law. Newton's third law of motion. Now, when you push an object or when you push, let's say, a supermarket trolley, the trolley experiences a force. The trolley is expected to apply an equal and opposite force on you. When you push on an object, the object experiences a force. The object is expected to exert or to apply an equal and opposite force on you. Newton understood that the body on which the force is exerted applies another force back on the body which is applying the force. So Newton was able to understand this. So when we have two bodies, let's say A and B, when body A applies a force on body B, according to Newton, he understands that body B must apply an equal and opposite force on body A. And this is exactly what we call Newton's third law of motion. So according to Newton's third law, whenever body A exerts a force on body B exerts an equal and opposite force on body A. That's what we call Newton's third law of motion. We shall use Newton's third law of motion many times in a unit called magnetic fields, maybe, gravitation. Those are A-level topics. So Newton understood that the body on which the force is exerted is expected to apply an equal or another force back on the body which is applying the force. And therefore, whenever body A exerts a force on body B is expected to exert an equal and opposite force on body A. That's what we call Newton's third law of motion. Of course, I know you might be familiar with this law by stating it that to every action there is an equal and opposite reaction. However, this statement is insufficient to state to refer to Newton's third law. When you say to every action there is an equal and opposite reaction, where is the action and where is the reaction? Could it be that the action and reactions are on the same body? So this statement does not highlight the very important point that action force and the reaction force act on two different bodies. This law has application in everyday life. For example, we walk because of this law. In one of the diagrams on this slide, you notice that there is someone walking here. Someone on how they call this? This is skating board. So for when we walk, we are walking because of Newton's third law. When you take a step forward, your foot presses against the ground. The ground is expected to exert an equal and opposite force on you. This is the force on you which propels you in your path. Talk about space rockets. Space rockets work because of the same law, Newton's third law. To expel the exhaust gases from the rocket exerts a force on the gases. The gases exert an equal and opposite force on the rocket, which accelerates the rocket forward, as shown in this diagram here. So I've given some two everyday experiences or everyday applications of Newton's third law. When you are walking, you walk because of this law. When you take a step forward, your foot presses against the ground. The ground then exerts an equal and opposite force on you. This is the force which propels you in your path. The space rockets work because of the same law. To expel the gases, the exhaust gases from the rocket exerts a force on the gases downwards. And the gases are expected to exert an equal and opposite force on the rocket upwards, which would accelerate the rocket forwards. So the force, if you are moving, stepping on the ground, the force from you could be the action, that is, you pushing on the ground. Then the force from the ground on you could be the reaction, the ground pushing on you, which propels you forward. So whenever body A exerts a force on body B is expected to exert an equal and opposite force on body A, and that is going to be Newton's third law of motion, and is the most important law in this unit. Now, one important thing you need to note is um, the two forces act on two different objects in opposite directions, but in the same line. The two forces are in the same line. Even when you look at the arrows that I have considered here, in these animation, these diagrams, these two are in the same line. They are two different bodies. The action is acting on the ground from the person. The reaction is acting on the person from the ground. So the two forces act on two different objects in opposite directions, but in the same line. That's why I say the statement that actions and reactions are equal but opposite is not enough to tell us that the two forces, the action and reaction, are acting on two different bodies. These two forces act on two different bodies, but they are in the same line. They act in the same line. So when I say if the force from body A is Fa, then it should be equal to the force on body B. The minus indicates that the two forces act in opposite directions. The equal signs indicates that the two forces are equal in magnitude. That is Newton's third law. Because this law is very important, we have to give more illustrations. So when two bodies interact, the forces they exert on each other are equal in magnitude and in opposite directions. The two forces that make up a Newton's third law pair have the following characteristics. Number one, the two forces act on different objects. They don't act on the same object. Number two, these are equal in magnitude. And number three, they act in opposite directions. And finally, these forces must be of the same kind, the same type. For example, let's consider yourself standing on the Earth's surface. Let's consider yourself standing on the Earth's surface. So, the Earth exerts a force on you, which is your weight, the gravitational force on you. This force acts at your center of gravity towards the center of the Earth. So that is going to be the pull of the Earth on you. Then the other pair which would constitute, the other force which would constitute the Newton's third law pair would therefore be your pull on the Earth, which pull originates from the center of the Earth. In other words, that is the weight of the Earth on you. So the two forces which constitute Newton's third law would be the gravitational force or the pull of gravity on you, which acts at your center of gravity, and your pull on the Earth, which acts at the center of gravity of the Earth. Then there are also other two forces. We have the contact force, the Earth on the man, and then we also have the contact force, the man on the Earth. So these two are equal and opposite. These two are equal and opposite, according to Newton's third law. So I can't say the weight of the man on the Earth and the normal reaction from the Earth on the man. That one cannot be Newton's third law pair because those two forces are not of the same type. But when I say the gravitational force, that is the weight of the man on the Earth and the weight of the Earth on the man, those two forces are of the same type. They are both gravitational. There's a pull of gravity on the man caused by the Earth. And according to Newton's third law, there will be a pull of gravity on the Earth caused by the man's mass. Those two are of the same type, so they constitute Newton's third law. Okay, so to elaborate this more examples on Newton's third law so that these questions are very common in multiple choice. Consider the ball in contact with the ground. The ball presses down on the ground. That is going to be maybe the action. The ground reacts to the ball upwards. That is going to be the reaction. So the force the ball exerts on the ground by pressing on it and the force the ground exerts on the ball by pushing it upwards, these two forces constitute a Newton third law pair. But the ball has a weight. So the Earth's gravity acts on the ball, that is the weight of the ball. Then the ball's gravity also acts on the Earth. So these two forces also constitute a Newton's third law pair. So I can't combine the force, the force, the pressing force on the ground with the Earth's gravity on the ball. That cannot constitute Newton's third law pair. The forces must be of the same type. So the Earth's gravity acts on the ball. In other words, the Earth's gravity pulls the ball downwards. The ball's gravity acts on the Earth. So the ball's gravity pulls the Earth upwards. These two constitute Newton's third law pair. The ball is in contact with the ground, so it is pressing against the ground. So that is the action. The ground must react by exerting a normal reaction force on the ball upwards. These two also constitute Newton's third law pair. So that is Newton's third law. Let's do a few, okay, I can add more description, more examples on Newton's third law because it is very important. Let's consider two cars in contact. A car in contact with, or a car which is pulling another carrier as shown in this diagram. So the car pushes the road backwards as the wheels rotate. And the road is expected to push the car forwards if there is enough friction, if the road is rough enough. Because if there is no friction, if the road is very smooth, the wheels may just slide instead of being pushed forward. So friction is important for us to move forward. So the car pushes the road backwards. In other words, the wheels push the road backwards. But because the road is rough, the road pushes the car forwards. Then at this point of contact between the car and the carrier behind, the car tends to pull the caravan forwards. So this force here, the car is tending to pull the caravan forward or the carrier forward. But the carrier is also not doing nothing. The caravan or the carrier pulls the car backwards. These two forces are expected to be equal but opposite, and of course, this will constitute what we call tension. The car is pulling the caravan forward, so this one is the force from the car on the caravan. This is going to be the force on the car from the caravan. This is the force on the caravan from the car, and this is the force on the car from the caravan. The two forces are equal and opposite. The two forces are of the same kind. That is what Newton's third law dictates. The two forces must be equal in magnitude. The two forces must be of the same kind. The two forces act on different bodies, and the two forces are supposed to be in line. That is Newton's third law. Here is a quick self-check. This is IGCSE. These are IGCSE questions. They just basically use Newton's second law of motion. I'll try to give a hint or try to give solutions to them. A force of 5 newtons is applied to a body of mass 3 kilograms. What is the acceleration? So the acceleration is equal to the force divided by the mass. You just press your calculator. 5 divided by 3. I think that is 1.7 meters per second squared. A stone of mass 50 grams is accelerated from a catapult to a speed of 80 meters per second from rest over a distance of 30 centimeters. What is the applied? What average force is applied by the rubber of catapult? So the average force we are talking about here is going to be the mass times the acceleration. All we need is the acceleration. So our final velocity is 8. It started from rest. Initial velocity was 0. So the acceleration is going to be final velocity minus initial velocity divided by time. We don't have the time, so I will use another formula. We have final velocity, initial velocity, and distance. So I'll use v squared equals to u squared plus 2as. We know the final velocity, initial velocity is 0. We know the distance as 30. 30 is 0.3 in meters. So it means the acceleration is going to be equal to v squared, which is 8 squared, minus u squared, which is 0 squared, divided by 2s, which is 2 times 0.3. So the acceleration is 8 squared divided by 2 times 0.3. So the acceleration is going to be 107 meters per second squared. So it means the force is going to be equal to 50, but is in grams, so it is 50 times 10 to the power of minus 3, then times the acceleration, which is 107, times 50 exponent minus 3. So the average force is about 5.3 newtons. An object of mass 1.5 kilograms is to be accelerated at 2.2 meters per second. What force is required? So we have this is supposed to be power minus 2, not power minus 1. That is acceleration is power minus 2, because that is an acceleration. So just substitute in the formula. Force is equal to mass times acceleration. Then a car of mass 1.5 exponent 3 kilograms traveling at 80 kilometers per hour is to be stopped in 11 seconds. What force is required? So all we need is to change the because if it is stopped, it means final velocity is 0. The time is 11 seconds. So all we need is to change 80 kilometers per hour into meters per second. So I will say 80 times 1000 divided by 3600. So this one is 22.2 meters per second. So of course the acceleration is going to be final velocity, which is 22.2 minus initial velocity, which is, final velocity of course is 0. But of course I just want a change in the velocity. So it is 22 minus 0 divided by 10, divide by 11. So divide by 11. So this is approximately 2.0, 2.1. Let me see, 22.2 divided by 11. 2.0 meters per second squared. That is the acceleration. Of course, this acceleration is negative, but the negative is not going to be used anywhere here. We just want to find the force. So the force is mass times acceleration. So it's 1.5 times 10 to the power of 3, then times 2, which is going to be 3.0 times 10 to the power of 3 newtons. So I say this acceleration is negative because we are traveling at 22.2 meters per second and it is finally stopped. Final velocity is 0. So I would have said is 0 minus 22.2 over 11. But because I just want the acceleration, which is the change in the velocity over change over time, I just go 22.2 minus 0 divided by 11. A motorcyclist of mass 60 kilograms rides a bike of mass 40 kilograms. As she sets off from the lights, the forward force on the bike is 200 newtons. Assume that the net force on the bike remains constant. Calculate the bike's velocity after 5.0 seconds. So they said the forward force is 200 newtons. They have not talked about friction here. Therefore, since they have not talked about friction, I would use this space up here. It means F is simply going to be 200 newtons. So I want to find acceleration. The acceleration is going to be the force, which is 200, divided by the total force, because it has a mass of 60 kilograms and the bike is 40. So I will divide this by 100. So the acceleration is 2 meters per second squared. And we want to find, assume that the net force on the bike remains constant, calculate the bike's velocity after 5 seconds. So I'll simply use V equals to, because the force is constant, the acceleration is constant. So V equals to U plus AT. So as she sets off from the lights, so that means initial velocity could be 0. So this is going to be 0 plus acceleration, which is 2 times time, which is 10, which is 5. This gives us V as 10 meters per second. So this would be the force. That would be the velocity after 5 seconds. A force 3 newtons acts on a body of mass 5 kilograms. Find the acceleration. That one is direct. You just substitute in the formula. Acceleration is force over mass. Find the force acting on a body of mass 12 kilograms and making it to produce an acceleration of 6 meters per second. So force is simply equal to mass times acceleration, as simple as that. So let's talk about mass and weight. Let's talk about mass and weight. Having stated Newton's laws, we now need to explore more about mass and weight. You might have talked about this in IGCSE. So let's just remind ourselves about mass and weight as it was mentioned in IGCSE. All along, we have already defined mass. You can define mass as the amount of matter in a body, the quantity of matter in a body, but we said mass is a property of a body which resists change in motion. A property of a body which resists change in motion. We defined mass as a measure of a body's inertia, if you recall. We defined mass as a measure of a body's inertia. So, we saw that mass is a measure of a body, of the amount of matter in a body, and is a property of a body which resists change in motion. A property of a body which resists change in motion. But I also want to recall something very important. All objects released near the surface of the Earth fall with the same acceleration, that is approximately 9.81. That is if air resistance is neglected or is negligible. Why is that possible? This is because the force causing this acceleration is the gravitational attraction of the Earth on the object, or the force of gravity. So, every object close to the Earth's surface will fall with the same acceleration, irrespective of their masses. Because the force pulling these objects is not depending on the mass of the objects, but is depending on the mass of the Earth. We shall see that in paper 4 in more details. But all objects released near the surface of the Earth, irrespective of their masses, will fall at the same rate, will fall at the same acceleration if there is no air resistance. Because the force causing the acceleration is constant and is the gravitational attraction, which depends on the mass of the Earth. In A level, we shall see that the gravitational field strength, or the acceleration due to gravity, is capital G times capital M divided by R squared, where capital G is the gravitational constant, or the universal gravitational constant. Capital M is going to be the mass of the Earth, not the mass of the object. And R is going to be the distance of the object from the center of the Earth. So the force, the gravitational force which acts on an object, is what we called the weight. So you should be able to define weight as the pull of gravity. The gravitational force that acts on an object is the weight. Even though mass is the property of a body which resists change in motion, weight is the gravitational force which acts on an object, is the gravitational pull on an object, that is weight. So now that's the difference between mass and weight. Of course, we have all along been knowing that weight can be calculated from mass times g, where mass should be in kilograms and g should be in newtons per kilogram, or meters per second squared. G is the acceleration of free fall, which you normally call acceleration due to gravity. That is letter G. The SI unit for weight is going to be newtons. Weight is the gravitational force. So weight is a force. Therefore, it is going to be measured in newtons. So the SI unit is the newton. Do not forget that G at this level will be given as 9.81 newtons per kilogram, or newtons or meters per second squared. Now, of course, it's not shocking as to why the units could be newtons per kilogram. Of course, newtons per kilogram is because if G is made the subject, G is weight divided by mass, where weight is a force measured in newtons and mass is measured in kilograms. So the units could also be newtons per kilogram. Okay, so that is a simple introduction about mass and weight. But before we leave this, I want you to note something. Because weight is a force and a force is a vector, then weight is a vector. The direction of weight is always towards the center of the Earth, vertically towards the center of the Earth, or vertically towards the center of the mass, which is creating the gravitational field. And a Newton balance can be used to measure weight in the laboratory, of course, especially if it is calibrated in newtons. So some commercial springs, especially the ones you find in the laboratory, have been calibrated in kilograms on one side and in newtons on the other side. So a Newton meter or a Newton balance could be used to measure the weight. But of course, when I say balance, basically I'm referring to mass. If I want to consider measuring weight, which is force, I would call the same instrument a Newton meter. Also, I want you to note that objects at rest also have weight. People think that when the object is at rest on the ground, it has no weight. It still has weight because the gravitational attraction on an object is the same whether it is falling or whether it is at rest on say, a table. The fact that an object rests on a table tells us, by Newton's first law, that the net resultant force acting on it is zero. So there must be another force acting on the object which balances its weight. Even when an object is resting on a table, even when an object is just resting on a table like this, it has weight. And since the object is not moving, then there must be another force. Since it already has weight, there must be another force which is balancing its weight. And this now takes us back to Newton's first law. If the net force acting on it is zero, there must be another force acting on the object to balance the weight. That's why we expect that there is another force which is acting upwards. This force must be equal in magnitude to the weight, but in opposite direction, and it could be called the normal contact force or the normal reaction force. That is, according to Newton's first law. That is not Newton's third law. Of course, Newton's third law, the weight, which would, if the weight is the pull of gravity on the center of the object, then the other force would be the pull of gravity from the center of the earth to the object. But the object is resting on a table. Therefore, we can just consider Newton's first law that if there is to be a net resultant force in this case, to balance the weight, there must be a normal contact force or a normal reaction force upwards. This force acts in the same vertical line, but this force, these forces act. This force, which is the normal contact force, must act in the same vertical line and should be equal to the weight to balance the weight if the net resultant force is to be zero for an object at rest. Okay, so here is a summary of weight, or the difference between mass and weight. So we have said mass is the quantity of matter in a substance, is a measure of is a property that resists change in motion. Weight is the pull of gravity on an object. We have seen mass is measured in kilograms and the weight is measured in newtons. Of course, we know that mass is a scalar quantity, but weight is a force, which is a vector quantity. And by the way, one important thing we need to note is that mass is constant everywhere. Your mass on the Earth's surface is going to be your mass on the moon. It is going to be your mass on another planet. But your weight is going to vary from place to place because weight is equal to your mass times the acceleration of free fall. The acceleration of free fall is not the same because the acceleration of free fall, as we shall see in A level, depends on the large mass which is creating the field. If you are on the planet, another planet, the mass of the planet is not the same as the mass of the Earth. Therefore, the acceleration of free fall on another planet is not the same as the acceleration of free fall on the Earth. And it also depends on the distance of the object from the center of the Earth, for example. If you go infinitely far away from the Earth, the value of g becomes smaller. That means your weight will change. So weight varies from place to place. Your weight on the equator is not the same as your weight on the poles because the distance between the center of the Earth to the equator is much bigger than the distance from the center of the Earth to the poles because the Earth bulges at the equator and it flattens at the poles. So the equatorial radius exceeds or is bigger than the polar radius. So we are saying our weight varies from place to place, and there are several reasons as why weight varies, but I've just mentioned g varies. There are reasons as to why g varies, which reasons we will mention in a unit called gravitation in paper 4. That is A-level physics. Okay, so that is the difference between mass and weight. you should be able to distinguish between mass and weight. But more important, you should be able to define mass and weight. And many times when the examiner says to say the difference between mass and weight and gives you three, or says distinguish between mass and weight and gives you 3 marks, the first 2 marks will be for defining mass and stating the weight, and defining weight. The second is either to tell us that mass is a scalar and weight is a vector, or tell us that mass is constant throughout the universe and weight varies from place to place. You should be able to be creative when answering such questions. Okay. So lastly, let's talk about non-uniform motion and terminal velocity in this case. Non-uniform motion and terminal velocity. What do we mean by non-uniform motion and terminal velocity? Of course, for uniform motion, we always assume that acceleration is constant throughout. So air resistance is normally negligible. But how about for non-uniform motion and terminal velocity? Of course, the word terminal means final, constant. It becomes constant. Okay. So the velocity of a body falling through a resistive fluid. Of course, a resistive fluid, a fluid where there is friction, I can say, or resistance in that case. The velocity of a body falling through a resistive fluid, it can be a liquid or a gas, or a body falling in air where there is air resistance. It does not increase indefinitely, but eventually reaches a maximum velocity, which we call the terminal velocity. If an object is falling in a fluid, either in air or a liquid, its velocity is said to increase because there is an acceleration. It could be acceleration due to gravity. But because of the resistance, the acceleration goes on reducing because the acceleration depends on the resultant force. So we are considering an object falling in a fluid. It has weight, but if it is falling in a fluid, there is a resistance to its motion in upwards. To find the acceleration is equal to resultant force is equal to ma, which will be now say the weight minus the force due to resistance. So because as the body falls in a fluid, before it starts falling, the resistance is zero. So the acceleration is going to be equal to the acceleration due to gravity. So let's say we are falling on the earth's surface. So it means ma is going to be mg, which is the weight, minus the force due to resistance. So before it starts falling, the resistance is zero. That means acceleration will just be equal to g. But when it starts falling, the resistance is not constant, it starts increasing from zero. That means the difference between mg and fr decreases, which means the acceleration goes on decreasing. So the velocity of a body falling through resistance does not increase indefinitely. Because the acceleration is decreasing, it means the increase in velocity is becoming smaller. Increase in velocity becomes smaller. The velocity is still increasing, but at a smaller rate until a point where it can't increase any further. That's the point where the acceleration is going to become zero and the velocity is going to become constant. So we are saying eventually it reaches a maximum velocity, which we shall call the terminal velocity. So when the body falls freely, its speed increases. That's what I've been saying here because there's an acceleration. As the speed increases, the force due to air resistance also increases in the opposite direction, remember. So the force of resistance increases with the speed. Initially, for smaller speeds, the force is directly proportional to speed. But later on, you might have seen in force density and pressure, when the speed is much bigger, force is directly proportional to the square. Resistance force is directly proportional to the square of the speed. So as the speed increases, the force due to air resistance also increases. When the resistive force has reached a value equal to and opposite to the weight. So if F resistance is equal to the weight mg, if mg is the same as Fr, it means ma will be equal to 0. So when the resistive force has reached a value and equal and opposite to the weight of the falling body, the body no longer accelerates but continues at a uniform velocity. So here it means the acceleration is going to be zero. It no longer accelerates, it no longer speeds up, but it will continue now at a constant velocity. This is the case of non-uniform acceleration. So the acceleration is not uniform because it was decreasing, it decreased to zero. So before we start with an acceleration of 9.81, if it was falling in air or close to the Earth's surface. But then finally it decreases to zero. And at the time when the terminal velocity has or is achieved. So when we reach terminal velocity, the acceleration has decreased from 9.81 to zero. When we talk about uniform motion, the acceleration would remain 9.81 throughout the motion. So this one is called non-uniform motion or non-uniform acceleration because the acceleration is decreasing until it becomes zero. And when it becomes zero, the body cannot accelerate any further. The speed or velocity cannot increase any further. So the velocity reached is going to be called terminal velocity, or the final velocity is terminal velocity, the maximum velocity. Hence, raindrops and parachutists are normally traveling at a constant or terminal speed by the time they approach the ground. So a parachutist will accelerate and reach a constant speed, and then will reach the ground with this constant speed. Normally, the speed is good enough for the parachutist to land without harming themselves. That is what we mean by non-uniform motion or non-uniform acceleration. Non-uniform motion or non-uniform acceleration. So the insects, the raindrops, and so on and so forth can be considered as some examples where we can think of non-uniform motion or non-uniform acceleration. So if we were to sketch a graph of velocity against time, how would it look like? So a velocity time graph for a body falling through a resistive fluid. You must also have seen this in a unit called kinematics. But if you haven't seen this, then I can talk about it here. So the terminal velocity depends on the weight and the surface area of the object. For example, if you think about insects, for insects, they are very light in weight. So air resistance is much greater for a human being, and so the terminal velocity is quite low for insects. The terminal velocity for insects is very low, so they just accelerate to a smaller distance. They just gain a smaller velocity and they reach terminal velocity because of their small weight. Yet for human beings, the terminal velocity is going to be bigger because of the weight of a human being. The human being will gain much velocity before reaching terminal velocity. And by the way, also I want you to note that air resistance increases as the square of the speed. Air resistance increases as the square of the speed. Even when it is in a fluid, the resistive force the drag force in a fluid increases as the square of the speed. And this is the reason why insects can be swept to several kilometers into the atmosphere by rising air streams, because air resistance increases with the square of as the square of the speed. So because insects have a smaller weight, they have a smaller terminal velocity, and since air resistance increases as the square of the speed, they can easily be swept into the air or swept high several kilometers into the atmosphere by raising air. So initially at t equals to 0, the speed is 0. We have not started moving. But as time goes on, the speed is increasing because there's an acceleration, which was initially 9.81. But as air resistance increases, the acceleration decreases. And if the acceleration decreases, the velocity is increasing but at a smaller rate. And finally, we shall reach a terminal velocity. So here initially, the velocity is still increasing, but here we can say the acceleration is decreasing. Remember, acceleration is equal to the gradient of a velocity time graph, that is change in velocity over time. So here the acceleration is still high, Here the acceleration is decreasing. You see the gradient is decreasing because the gradient is the tangent to this curve. And here the acceleration is equal to 0 because it is a horizontal line and the gradient is 0. So a velocity time graph for a body falling in a fluid, either in air or in a liquid, is going to look like this. Just to explain it, consider an object whose weight is W and W equals to mg. It is falling in air. At t equals to 0, the force due to air resistance equals to 0. So it means the resultant force F is equal to ma, which is equal to mg. So A is equal to g. That is at t equals to 0. After some time, as time goes on, the weight does not change, but the air resistance starts increasing. So after some time t, the force due to air resistance, let me call it F air, is going to be balancing with the weight mg. At that point, the resultant force ma is equal to mg minus the force due to air resistance. But at this time, the force due to air resistance is equal to mg, which means this part here is going to be 0. And when ma equals to 0, it means the acceleration is equal to 0 because the resultant force will be 0. And this means the velocity is going to be constant. And that constant velocity is what we call the terminal velocity. So a graph of velocity against time, a body falling in a fluid, either air or a liquid, is going to be like this. A curve with a decreasing gradient, which finally becomes horizontal. That is when the acceleration becomes 0. Of course, the resultant force becomes 0 because the air resistance is equal to the weight acting on the weight of the body, and the velocity is constant. And that's what we call terminal velocity. You must understand this because you should be able to explain most of the questions or many questions involving this concept. Okay, so let lesson 1 end here. See you in lesson 2. Until next time, bye bye.